So today I would like to provide you some new insights into large batch training and show how to apply these insights and to improve the training on modern hardware. So what's the modern hardware I'm talking about? It's typically something like accelerators, GPUs, TPUs, and like computing clouds, like computing clusters. So all this hardware, commonly have a huge or massive computing parallelism. So with the access to this strong, powerful computing resource, the central problem of modern machine learning practice is about how to effectively use the parallelism for modern training. Okay, here the training I'm talking about is basically stochastic gradient descent, right? So if you take a look here, there's one iteration of stochastic gradient descent. You just first subsample a mini batch of training data, that's its size of m, and then you calculate corresponding gradient. And then you rescale this component by the step size adder and apply this to update your parameters. Okay, the best practice to apply this SGD iteration on a modern hardware to effectively utilize the parallelism is basically starts with choosing a very large batch size. So by doing so, normally you are able to fully utilize the underlying hardware, and it allows you to possibly minimize the training time. Well, in reality, this practice is not enough. It's not enough to just choose a large batch size. So what we normally do is we also need to apply the so-called linear scaling rule. So instead of just choosing large batch size, we also need to scale the learning rate accordingly. So this rule says, like, when we multiply or increase the batch size by a factor of k, we should also increase the step size or learning rate by a factor of k. Okay, so, but why do we want to apply this? So this rule allows you to really train the model with a much larger batch size, but still converge in nearly the same number of epochs or equivalent computation. However, many empirical evidence has shown like there is an upper limit for this rule. Like there's the limit of linear scaling, which we just call it m star. And in our recent paper, we show like analytically we can calculate this m star from a formula, and also the training time, the walk-off training time has this correlation with the batch size. So when you choose a batch size m that's smaller or equal to m star, your training time is going to be almost linear to 1 over m, which implies that when you double your batch size, you can almost half your training time. This is assuming you have enough computing resource. But when you choose any batch size that's larger than m star, the training time is almost a constant by a small factor. Okay. So in this talk, I would like to move one step forward. So not just to calculate or identify this limit of linear scaling. I would like to really extend the linear scaling to match the parallelism of the computing hardware. So it allows us to further minimize the training time. So I would like to present the first principle solution that extends the linear scaling to effectively utilize the parallelism. And this idea is really demonstrated on a class of kernel machines. And we easily achieve like a 10 to 100 times speed up on a single GPU over the state-of-the-art other kernel methods. And we also fully automate the parameter selection during the training. Okay, before I talk about like how we're extending the linear scaling, let's first take a look how can we minimize the training time for a standard SGD. But it's in fact turns out to be very simple. We just need to choose the optimal step size, learning rate, and the batch size. And in our recent work, we show like we can calculate the optimal step size for a given batch size explicitly. So now the problem becomes simpler, right? We just want to choose a batch size m to minimize the training time. And before we talk about how to do the minimization, let's break the training time into two parts. The first part is the number of epochs you need to converge to certain training loss. And second part is just the walk-off time to train one epoch. So the second part really depends on hardware and your model architecture. Okay, it turns out like this correlation is very simple. So this curve, the x-axis is batch size, and the y-axis is the number of epochs for convergence. So it basically capture the linear scaling rule, right? So here m star is the limit of linear scaling. We calculated it explicitly. And if you choose a batch size before m star, so the number of epochs you need is almost a constant by a small difference, like 10%. And when you go beyond m star, it turns out you need a much more number of epochs to converge to the same training loss. So the number of epochs after m star is almost linear to the batch size m. Okay. And we have a similar relationship between the batch size m and the time to train one epoch. So it's even easier. It's, if you increase your batch size m, right, the computation for one iteration, there's more parallelism inside. So you are able to have a higher utilization of the computing resource. So which translates just like a smaller time, like a less time to train one epoch. And here we identify a special point. It's called mGPU. It's nearly it's basically the smallest batch size that allows you to fully utilize your computing resource. Okay, now we are able to really show you how the training time, the walkout training time is changing with the change of the batch size, which is very simple. Just do a multiplication. And here you can see, like, normally you want to choose a batch size. In order to minimize the training time, you want to choose a batch size between this m star and mGPU. Okay, so it's simple. But there's a fundamental problem with this kind of best practice. And let's first just identify two regions in the training time figure. So the red region of this figure is what we call effective computation region. So if you choose a batch size here, you're able to converge in the minimum number of epochs. And this blue region, we call it full utilization region. So if you choose a batch size here, you're able to fully utilize your computing resource. Well, I mean, in practice, we normally have m star that is smaller than mGPU. The reason is, like, you probably do not just have one single GPU. You can have 10 GPU, 100 GPU, or 1,000 GPUs. So your computing parallelism could be much higher. And that ends up like we have to choose a batch size in this white region to minimize the training time. Well, that directly leads to underutilized computing resource, right? So we are unable to fully utilize the resource. Well, ideally, what we really want is something like m star that is larger or equal to mGPU. So in this case, these two regions will overlap. Right? So if you choose a batch size in between this overlapped region, you're able to converge in the minimum number of epochs and still fully utilize your computing resource. Okay, so here comes our idea. So we want to always have this desired situation. And our solution is very straightforward. We just increase the m star to be as large as mGPU. So the limit of linear scaling could be always larger than the computing parallelism provided by the hardware. So we implement this idea for a class of kernel machines. And the kernel machine we consider here, you can think it's like a linear model with some nonlinear activation function. So alpha is like the model parameter you're trying to learn. And to apply this idea, what we do is we simply learn an adaptive kernel by spectrum modifying the original kernel. So, but more specifically, what kind of kernel are we trying to learn? So we want to learn a kernel that allows us to have the exact same optimization, optimal solution as the original one, but extending the linear scaling to something much larger. So the approach, again, is a spectrum modification. And the limit of linear scaling for the original kernel here is simply 1 over lambda 1. So what is lambda 1? It's essentially the top eigenvalue of the original kernel matrix, which can be shown in this blue curve. So the blue curve is essentially the eigenspectrum of the original kernel matrix. And so what we want to do is we want to do a spectrum modification of that kernel function. So its spectrum becomes this orange curve. So it's like a flatten of the eigenspectrum. And by doing so, the new kernel will have a different corresponding limit of linear scaling, which is just 1 over lambda q plus 1. And it implies a directly increase of the m star by a factor of lambda 1 over lambda q plus 1. So in the older paper, like by our group, we show like this lambda 1 over lambda q plus 1 can be super polynomial in regard to q. So it's a huge. With like a few tens q, like this eigenspectrum flattening, you can have a few thousand increase in largest mini batch size you can achieve. Okay, but so what does this affect? How does this affect the final training time? And ideally, it's basically showing this cartoon, and you can see this dotted line is about the original kernel. Again, this x-axis is the batch size, and the y-axis is the training time for convergence. So for the original kernel, you can decrease your training time by increase your batch size up to this m star, which is, we know is small. And the new kernel simply will just extend this linear scaling region. You can keep increase your batch size until like m GPU. So your new limit of linear scaling is as large as an m GPU. So you can further drive down the training time. But how does this work in practice? So here we just show you a simple example with for the speech recognition task. So this blue curve, again, is from the original kernel. And here, again, the x-axis is batch size, y-axis is the training time for convergence. And we can see, like, for the original kernel, the optimal batch size is around 16. Right? But for the new kernel here, we can drive down this optimal batch size to around 6,000. So this directly provides us on a single GPU like 30 times speed up. And let's take another look in this curve. So basically, we see like we reach the full utilization of the GPU at around the mini batch size of 256. But our m star now is around 6,000. So which implies we can probably utilize 20 GPUs at the same time and achieve another 20 times speed up. Okay, we package the entire this algorithm and this implementation in this pipeline. The nice thing about this pipeline is it is fully automatic. So all you need is, as a user, is to input this training data, the kernel function you select, which is basically a model architecture, and some information about the hardware you're using, like a memory size or the computing cores you have. So this pipeline will just automatically construct a new kernel and apply it for training. So it allows you to automatically extend the linear scaling to mGPU. And what's even moreover, it has a negligible overhead. So in our experiments, the overhead is like 2 or 3%, which is totally negligible. Okay. So here we show you another set of experiments on some small data set. And we call this interactive training. Because on this data set around 100,000 samples, we are able to finish the training in just 10 seconds, around 15 seconds, really. So in comparison, we compare our result to other libSVM and GPU implementation of libSVM. We see like at least 10 to 20 times speed up. So these experiments on GPU are, so for SundaeSVM is an implementation of libSVM on GPU. So we do this experiment on the same GPU. So this interactive training allows us to try different kernel functions and different kernel parameters quickly, right? So it somehow achieves the same effect as the AutoML. Okay, I also compare our results like to other state-of-the-art kernel methods on some larger data sets. So overall, we are able to improve the training time from like hundreds of thousands of CPU computation hours to like minutes of GPU computation. So I want to highlight like the result with the ImageNet. So we train a full ImageNet on a single GPU in around 40 minutes. So we also compare like results with a block coordinate descent, which is a kind of a strong result. So we see like we are able to finish training on a single GPU in 80 minutes. In comparison, their method will take a few thousand hours. So what's more interesting is we are able to achieve a slightly higher test accuracy. Okay. So here I would like to talk about the take-home message. So we have the first principle solution to extend linear scaling. I think that's the original people didn't realize this. Like we just want to identify the limit of linear scaling by experiments or by some heuristics. But in fact, now I show like we can really extend it to something like much larger. In this case, in our experiments, we extend the linear scaling around 1,000 times. So it will allow us to effectively utilize the massive parallelism in the computing resource. Of course, this will translate to like a significantly reduction in training time. So our method is only demonstrated on these kernel machines, but in fact, it's more general. But on these classical kernel machines, we're able to scale the kernel models to very large resource. And this was not possible with kernel models when applying like a mini-batch SGD. So it also allows us to rapidly do this parameter selection. So nowadays, like we basically choose all the kernel functions and parameters automatically in our experiments. I also would like to propose, like when we do the research in optimization, this kernel model should be like a sanity check, because it's the simplest modern model that has a very nice performance. And it's in fact very comparable to neural networks. So first of all, it's overparameterized. And secondly, it has many theoretical connections to the generalization performance of different kinds of neural networks. Okay, that's the end of my talk. Okay.
Thank you. Questions, please? Don't forget to say your name and affiliation. Questions? Yeah, please.
Yeah.
My name is Yokoyama from NEC Corporation.
Hi.
I'm wondering the accuracy comparison between your method and LibSMM or standard SVM, because
Right.
LibSMM is implemented by the different optimization method called the SMO. So
yes, yes, yeah. They were doing SML, so it's kind of it's not for comparison. It's more like a reference.
reference.
Yeah.
In your paper.
No, what I mean is like they implement the SMO, so for standard SVM, and we implement the really SGD. So these are two different methods, that's true.
So get to the compared to the different accuracy, right? Or same?
Oh yeah, that's a question, yeah. So it's the same accuracy on
accuracy.
a training loss, and we in fact have a very comparable testing accuracy as well.
Okay, thank you.
Hi, this is Gauri Joshi from Carnegie Mellon. Really nice talk. My question is that you're using these methods to increase the optimal mini batch size where we can operate. So are you also then using a much higher learning rate, proportionally larger learning rate for the experiments that you showed?
Okay, so the question is like, do we change the learning rate when we change the batch size? So yes,
Yeah.
so we essentially this is essentially like extending the linear scaling. So we apply the same linear scaling. So when we increase the batch size by a factor of, let's say, 100 times, we also increase the learning rate by a factor of 100 times.
Oh, okay. I think that makes it very clear. So that's why I think you're getting such big speed up. But the key thing is making the mini batch size bigger.
Yeah, exactly. But like before, if you don't apply our method, you cannot really increase your learning rate because it will diverge.
Yes, I understand. Thank you.
Yeah, thanks.
Great. So let's thank the speaker again.